of really epic stuff happens when a star dies. If the star's core is less than 1.4 times the mass of the sun, it becomes a white dwarf, a very hot ball of super compressed matter about the size of the Earth. If the core is heftier, between 1.4 and 2.8 times the sun's mass, it collapses even further, becoming a neutron star that's only 20 kilometers across. The neutron soup inside of it resists the collapse and prevents the core from shrinking anymore. But what if the mass is more than 2.8 times the sun's? If that happens, the gravity of the core can actually overcome the tremendous resistance of the neutrons and continue its collapse. What force can possibly stop it now? It turns out none. None more force. There is literally nothing in the universe that can stop the collapse. The core of the star is about to go bye-bye. Way back in episode 7, I talked about escape velocity, and it's about to become a major player in the unfolding events of the collapsing core of a high-mass star. In brief, it's the velocity at which you need to fling something off the surface of an object to get it to escape. For the Earth, the escape velocity is about 11 kilometers per second. Get something moving that quickly, and it's gone. It'll never fall back. The Sun, which has much stronger gravity than Earth, has an escape velocity of over 600 kilometers per second. A neutron star, with its immense gravity, can have an escape velocity of 150,000 kilometers per second. That's half the speed of light. Keep that in mind, and let's go back to the collapsing core of the star. As it shrinks, its gravity gets stronger and stronger. That means its escape velocity gets higher and higher. When it's neutron star size, the escape velocity is half the speed of light. But if it's more than 2.8 times the mass of the sun, the core will keep collapsing. When its size drops just a little bit more, down to roughly 18 kilometers, an amazing thing happens. The escape velocity at its surface is equal to the speed of light. And, well, that's a problem, because in our universe, nothing can travel faster than the speed of light. Not a rock, not a rocket, not even light itself. Once the core of the star shrinks down smaller than that magic size, nothing can escape. No matter can come out, so it's like an infinitely deep hole. And no light can come out, so it's black. We should come up with a snappy name for such an object. A black hole is the ultimate end state for the core of a high-mass star. Whatever happens in a black hole stays in a black hole. That region of space, that surface around the black hole where the escape velocity is the speed of light, is called the event horizon. For that reason, any event that happens inside can't be known. It's beyond the horizon for us. Black holes mess with our concepts of space and time. The math and physics of black holes is incredibly complex, so much so that even after several decades of study, physicists still argue over a lot of their properties. This has led to a lot of misconceptions about them, too. All right, let's get this out of the way right now. The sun cannot become a black hole. It takes a stellar core at least about 3 times the mass of the sun to overcome neutron degeneracy pressure. That means the original star must have something like 20 times the sun's mass or more. So we're safe from that particular sci-fi scenario. Here's another misconception. A lot of people think of black holes as cosmic vacuum cleaners, sucking in everything near them. But that's not really true. They have powerful gravity, yeah, but only when you're very close to one. The power of a black hole comes from its mass, certainly, but just as important is its size, or really, its lack of size. If you could turn the sun into a black hole, which you can, but let's pretend you could, then the Earth would orbit it pretty much exactly as it does now. From 150 million kilometers away, the Earth doesn't care if the sun is big or tiny. We're so far away that it doesn't matter. It gets to be a big deal when you get close. Remember from episode 7 about gravity, the strength of gravity you feel from an object depends on how massive it is and your distance from its center. The closest you can get to the sun is by touching it, being on its surface, about 700,000 kilometers from its center. If you get any closer to its center, you're inside it. The material outside of your position is no longer pulling you down, and so the gravity you feel will actually decrease. But if the sun were crushed down to about 6 kilometers across, it would be a black hole. You could get much closer than 700,000 kilometers to it, and as you did, you'd feel a stronger and stronger pull as you approached it. So, from far away, a black hole with, say, 10 times the sun's mass would pull on you just as hard as a normal star with that same mass. You can orbit a black hole too, as long as you keep a safe distance between you and it. Orbiting a 10 solar mass black hole would be just like orbiting a 10 solar mass star. except not so hot and bright. Black holes are weird enough without the misconceptions. Black holes also come in different sizes. The kind of black holes I've been talking about have a minimum mass of about 3 times the sun's, and might get as high as a dozen or more times the sun's mass, if the parent star was big enough. We call these stellar mass black holes. If it happens to gobble down more matter, it gets more massive, and the event horizon grows as well. The black hole gets bigger. The idea that huge black holes could form in the centers of galaxies was first proposed in the 1970s, and it wasn't much later that the first one was found in the center of our own Milky Way galaxy. We've measured its mass at a whopping 4.3 million times the sun's mass. And now we think every major galaxy has one at its heart too, and in fact may be crucial in the formation of galaxies themselves. I'll discuss those more in a future episode. Here's a fun thought. What would happen if you fell into one, say a stellar black hole with 10 times the sun's mass? You'd die. But what happens in the few milliseconds before you leave the known universe forever is actually pretty interesting. As we've seen many times in our own solar system, tides are important. They arise because gravity weakens with distance. So a big object like a moon gets stretched by its planet's gravity. The far side of the moon is pulled less than the near side. A black hole has incredibly intense gravity, so the tides it can inflict are serious indeed. They're so strong that if you fell into a stellar mass black hole feet first, the force of gravity on your feet can be millions of times stronger than the force on your head. Remember, even the meager tides of a planet can rip moons apart. When you multiply that force by 1,000,000, you're in trouble. As you fall in, your feet are pulled so much harder than your head that you stretch, pulled like taffy. You'd become a long, thin noodle, kilometers in length, but narrower than a hair wide. Astronomers call this, and no, I'm not kidding, spaghettification. This would happen pretty close to the black hole, just a few dozen kilometers out. If you fell in from a long distance, you'd be moving pretty near the speed of light by that point, and you'd only have a millisecond or so before it killed you anyway, so yay? Note that this is only for stellar mass black holes. Supermassive black holes are far bigger, millions or billions of kilometers across. Compared to that size, the distance between your head and feet is small, so the tides across you aren't nearly as severe. You'd fall in pretty much intact, if that makes you feel any better. But compared to either flavor of black hole, a star still has substantial size, and one that gets too close to any black hole can be disrupted via tides. In March 2011, astronomers witnessed just such an event. In a distant galaxy, a star apparently got too close to a black hole and was torn apart by the ferocious tides. As the star was disrupted, it flared into brightness, momentarily blasting out 1,000,000,000,000 times the sun's energy. That's how we were able to see it, even though it was several billion light years away. But I've saved the weirdest thing for last. One of Albert Einstein's biggest ideas is that space isn't just emptiness. It's an actual thing, like a fabric in which all matter and energy is embedded. What we perceive as gravity is really just a warping of this space, like the way a bowling ball on top of a bed warps the shape of the mattress. The more massive an object, the more it warps space. Not only that, but space and time are basically two parts of the same thing, what we now call space-time. You can't affect one without affecting the other. Einstein calculated that when a massive object warps space, it also warps time. Someone deep inside the gravitational influence of an object perceives time as ticking more slowly than someone far away from that object. I know, it's bizarre. We think of time as just flowing, and everyone should see it move at the same rate. But the universe is under no obligation to obey our preconceptions. Einstein was right. He was right a lot. This slowing of time is stronger the stronger the gravity of the object is. So your clock ticks a bit slower than someone far away from Earth, for example. The effect is tiny but real, and we've actually measured it on Earth with extremely precise clocks. However, if you get near a black hole, the effect gets a lot stronger. In fact, black holes warp space-time so much that at the event horizon, time essentially stops. You'd see your clock running normally, and you'd just fall in. Bloop, gone. But someone far away would see your clock ticking more slowly as you fell in. And this isn't a mechanical or perception effect. It's actually woven into the fabric of space. To someone outside looking down on you, your fall would literally take forever. But then they wouldn't be able to actually see you. The light you emit would have to fight the intense gravity of the black hole to get out. And to do that, it would lose energy. This is very similar to the Doppler redshift I've talked about in earlier episodes, and it's called a gravitational redshift. When you're right at the event horizon, just when an outside observer would see your clock stop, They'd also see the light coming from you infinitely redshift. Your light would lose all its energy trying to leave the vicinity of the black hole, and you'd be invisible. And from your viewpoint, buckle up, because this is wow. You'd see the universe speed up. And just as you hit the event horizon, all of time would pass. All of it. And all that light coming at you from the universe would be blue shifted, becoming such high energy that you'd be fried. But since you're about to fall into a black hole, you probably wouldn't care. See? Like I said. Wow. Black holes are so strange, with such fiercely complicated math and physics to explain them, that scientists are still trying to figure out even basic things about them. For example, some scientists argue that the event horizon as we understand it may not actually exist, and that when you apply quantum mechanics to black hole physics, you find particles can slowly leak out. We're still new at this and struggling to understand what may be the most complex objects in the cosmos. Black holes, as bizarre and counterintuitive as they are, keep popping up from here on out as we poke our noses into more and bigger astronomical objects. While they may seem scary and weird, and let's be honest, they are, they have literally shaped most of the objects we see in the universe. Today you learn that stellar mass black holes form when a very massive star dies and its core collapses. The core has to be more than about 2.8 times the sun's mass to form a black hole. What is the nature of the universe? How's that for a question? For a long time, we humans had no idea what was going on in the universe. To help, we made up stories to either help us explain what we saw or to make us feel better about what we didn't understand. But then science came along and we started to understand more. We could test our ideas, and as we got more confident in the process, our ideas grew. The field of cosmology was born, the study of the cosmos itself. And now, after centuries of speculation and just so stories, we're starting to get a grasp on the biggest ideas there are. What is the nature of the universe? Let's find out. By the turn of the 20th century, scientists knew the Earth was old. Darwin's theory of evolution strongly implied the Earth was at least millions of years old, and Lord Kelvin, a hugely respected physicist and engineer, confirmed the Earth was ancient, given that it must have cooled from an initially molten state. That takes a while, at least 1,000,000 years. How old exactly, no one knew. As for the universe itself, it logically must be as old or older than Earth. A popular model for the universe was that it was static. It is and always has been as we see it now, and in general hasn't changed. Stars may be born and they may die, but overall, things pretty much stayed in balance. The universe always existed, always will, always had galaxies in it, and so on. There are variations on this idea, but that's it in a nutshell, and it's what many astronomers believed. This is important. When we try to understand observations in astronomy, we fit them into a framework of understanding, things we think we already know. When something doesn't fit, it's a problem. Maybe the observation is wrong, or maybe we're misinterpreting it, or maybe the framework is wrong. That's a big step to undertake and needs proper contemplation and skepticism. Science is a tapestry, and when you yank at one thread, the whole thing may need reweaving. Sometimes, rarely, but sometimes, you have to yank that thread. The thread that got pulled in this picture was first uncovered in 1912. That was when astronomer Vesto Slipher, who has the uncontested coolest name for an astronomer ever, started taking spectra of the so-called spiral nebulae, hoping to get some insight on their characteristics. Remember, this was before we understood what galaxies actually were. It took him several years of observations, but by 1917, he had observed 25 of them, and he found something astonishing. When he examined their spectra, he saw that almost all of them were highly redshifted. In other words, it looked like most of these objects were rushing away from us at high speed, millions of kilometers per hour. What could that mean? At this point, two different lines of work began to converge. One was by a Belgian theoretical physicist named Georges Lemaitre. In the 1920s, he had been studying Albert Einstein's work, the equations dealing with the behavior of the universe as a whole. Einstein had concluded that the universe was static, unchanging, but Lemaitre disagreed. He found that an expanding or contracting universe fit the equations better, and given the redshifts observed by Slipher, he proposed the universe itself was getting bigger, which is why the galaxies appeared to be moving away from us. Another brilliant physicist, Alexander Friedmann, had also reached the same conclusion. At the same time, astronomers were trying to determine the distances to the nebulae, now understood to be galaxies in their own right. As I mentioned in our first episode about galaxies, Edwin Hubble and his assistant Milton Humason were at the forefront of this. They observed variable stars in the Andromeda galaxy that allowed them to get the distance to the galaxy. They then observed some of the same galaxies Slipher did and measured their distances. When they compared distances to the redshift Slipher observed, they found that the farther away the galaxy was, the faster it was moving away from us. Let me repeat that because it's kinda important. The farther away a galaxy was, the faster it appeared to recede from us. Some other astronomers had also found similar results, but the work of Hubble and Humason clinched it. We now know it to be true for every distant galaxy we observe. They are all redshifted, all heading away from us. And this ties into what Lemaitre had concluded. The universe is expanding. Wait, what? The universe is getting bigger? How can that be? What does that even mean? There are lots of different ways of looking at this. Lemaitre himself suggested imagining the cosmic clock running backwards. Right now, as time inexorably marches on, all the galaxies in the sky are getting farther and farther away from us. But that means that in the past, they were closer together. Run the clock back far enough, and they get closer and closer together until at some point in the past, everything in the entire universe was crammed together into an uber-dense thing. That is a really, really weird thought. It's hard to imagine everything in the whole cosmos, every star, nebula, galaxy, every atom, electron, and proton, all squeezed together into one infinitely dense blob. But that's what the observations are telling us. Lemaitre called this a primeval atom, or more colorfully, the cosmic egg. Fair enough, but this has implications. If you squeeze all the energy everywhere into one place, that place is going to be hot. When the universe was a tiny dot, it would have been unimaginably, hellishly hot. Then, for some reason, it suddenly expanded violently and started cooling. This sounds an awful lot like an explosion. Bang! Involving the entire universe, which is big. What else would you call this but the Big Bang? In fact, the term became popular when astronomer Fred Hoyle used it on a radio show and later in a widely read magazine article. Ironically, he meant it somewhat disparagingly since he didn't think the Big Bang model was correct. To his and many other astronomers' chagrin, the name stuck. I like it. It's not perfectly accurate, but it's succinct. Again, this is all pretty strange, and astronomers had a hard time accepting it. After all, it went against everything they thought was true at the time. In science, though, a hypothesis needs to make testable predictions before it can be taken seriously. What predictions could the Big Bang model of the universe make that we can observe today? The speed of light is fast. 300,000 kilometers per second, or about 1 billion kilometers per hour. Like I said, fast, but not infinitely fast. The sun is 150 million kilometers away. It takes light about 8 minutes to reach the Earth. So in a sense, you're seeing the sun as it was 8 minutes ago. The nearest star system to us is Alpha Centauri, 4.3 light years away. So we see it as it was 4.3 years ago. The Andromeda galaxy is about 2.5 million light years away. The light we see from it now left that galaxy when Australopithecus walked the Earth. The farther away something is, the farther in the past we see it. This is called the look-back time, and it's a crucial tool for cosmology. By observing very distant objects, we can see the universe when it was young. You might think that we could see all the way back to the moment of the Big Bang. But there's a problem. At some point back in time, the universe was so hot and dense that it was the same temperature as the surface of a star. It would have been very luminous, but also opaque. As it expanded, it cooled and became transparent. If we look back far enough, that moment in time when it cleared up is as far back as we can see. What does that moment look like? By looking at the physics of the Big Bang, the math that describes how matter, energy, space, and time behave, astronomers could predict when this moment happened in the lifetime of the universe, a few 100,000 years after the bang itself. Using the idea of look-back time, they could predict how far away it would be from us and therefore calculate its redshift. Remember, redshift stretches the wavelength of light. The light the universe emitted at the time would have been like a star in the visible part of the electromagnetic spectrum. But the light that reaches us billions of years later, now, should be redshifted into microwave wavelengths. In 1965, a pair of radio astronomers announced they had found a signal in their radio telescope that was like a background noise coming from everywhere in the sky. They tried everything they could to explain it, including scraping out the bird poop inside their radio telescope in case that might be causing it. But the only thing that made sense was that this was indeed the redshifted light from the early universe. They had discovered the glow of the fireball left over from the birth of the cosmos. Later, in the 1990s, satellite observations further refined the measurements of this cosmic microwave background, and now it's essentially confirmed. This glow was successfully predicted by the Big Bang model, and now we see it in exquisite detail. Its discovery was a huge step in cosmology. The redshift of distant galaxies and the cosmic background are not the only confirmations we have that the Big Bang model is correct. For example, the model also makes predictions about the elements we see in the universe. At first, when the universe was dense and hot, only subatomic particles could exist. But as the universe cooled, for a brief time, they could fuse and form heavier elements. The Big Bang model predicts certain abundances of elements, ratios of them compared to hydrogen, and that's just what we see in the universe at large. Also, the sizes and shapes of the largest structures in the cosmos are in line with what a Big Bang model predicts. There's lots of other observational evidence as well. Pretty much every modern astronomer on Earth understands that the Big Bang model of how the universe got its start is the correct one. But what does it mean? I mean, physically, it's a very common misconception that the Big Bang was an explosion in space with everything rushing away from some point. But that's not what's really happening. Remember, I've talked about space being a thing in which matter and energy exist. Space can be warped or bent by mass, creating what we think of as gravity. When we talk about the universe expanding, we mean space itself is expanding, and when it does, it carries galaxies along with it. In a sense, it's like having a rubber ruler. When you pull on it, it gets longer, and the distance between the tick marks gets wider. When the ruler doubles in length, the tick marks that started out a millimeter apart are now 2 millimeters apart. But tick marks that were 10 centimeters apart are now 20 centimeters apart. In other words, the farther away a tick mark is, the faster it appears to move away. Sound familiar? That's just what galaxy redshifts are telling us. It also means that really the galaxies aren't actually doing any moving. It's that space between them is expanding. This may seem like a nitpicky semantic point, but it's physically true. The galaxies are, for all intents and purposes, standing still. The space in between them is where all the action is. And it gets even weirder. This is true no matter where you are in the universe. From any galaxy, it looks like all the others are rushing away from you. Look back at that ruler. No matter what tick mark you start with, when the ruler stretches from that spot, it looks like the tick marks are all moving away from you. This is what Einstein's equations showed and what Lemaitre saw in them. Space is expanding. But that means the Big Bang wasn't an explosion in some pre-existing space. It was the initial exploding expansion of space itself. The universe isn't expanding into anything because it's all there is. There's nothing outside the universe for it to expand into. This also means the universe has no center, no point of origin. Imagine the ruler is now a circle and the diameter is expanding. No tick mark is the actual center, yet no matter where you are on the ruler, every tick mark appears to move away from you. In a similar way, every spot in the universe appears like the center, which means none is. No place in the universe is more special than any place else. We're all in this together. It can be hard to grasp, and I'll admit we all have some difficulty with these concepts, but the math bears them out, and so do essentially all the observations we make of the distant universe. And in all this weirdness, don't lose sight of the big picture. The universe had a beginning, and we can see evidence of it. Not only that, but by measuring how quickly it's expanding, we can use math to run the clock backwards and determine the age of the universe. Currently, the best measurement we have of the age of the universe is 13.82 billion years. Or perhaps I should say, 13.82 billion years. That's an amazing number. It's a long, long time, 3 times older than the Earth. But what gets me is that we can figure it out at all. Pretty smart, us apes. Today you learned that distant galaxies show a redshift in their spectra, which means they're moving away from us. The universe is expanding. This means it used to be hot and dense, then it started expanding and cooling. Hey folks, Phil Plait here, and for the past few episodes, I've been going over what we know about the structure, history, and evolution of the universe, and how we know it. Now it's time to put that into action. We can use this knowledge of physics, math, and astronomy to figure out what the universe was like in the past, going all the way back to literally the first moment after it was born. So, here you go, a brief history of the universe. In the beginning, there was nothing. Then, there was everything. Oh, you want more? It may seem a little weird to suppose that we can understand how the universe got its start, But it's much like any other field of science. We have clues, observations based on what we see going on now. Knowing the rules of physics, we can then run the clock backwards and see what things were like farther and farther into the past. For example, as I've talked about in the past couple of episodes, the universe is expanding. That means in the past it was denser, more crowded, and hotter. At some point, it was hotter than the surface of a star, hotter than the core of a star, hotter than the heart of a supernova. And as we push the timer back even farther, we find temperatures and densities that make a supernova look chilly and positively rarefied. A lot of what we know about the early universe comes from experiments done in giant particle colliders. When the cosmos was very young and very hot, particles were whizzing around at high speeds and slamming into each other, creating other subatomic particles in the process. That's exactly what colliders do. The higher energy we can give our colliders, the faster we can whack particles together, and the earlier the phase of the universe we can investigate. That's one of the main reasons why we keep making them bigger and more powerful, to test our ideas of what the young cosmos was like. So let's wind the clock back. Looking around us, peering into the universe, both near and far, what can we say about the beginning of everything? When the universe got its start, it was unfathomably hot and dense. It was totally different than it is today, because when you pump more energy into something, the way it behaves, even its fundamental physical nature, changes. If you take a snowball and heat it up, it'll melt. We call that a phase change or a change of state. Heat it more and it vaporizes, changing into a gas. It's still water, still composed of water molecules, but it looks and acts pretty differently, right? When you heat something up, what you're doing is giving it more energy. In a solid, this means the atoms wiggle around more and more until they break free of their restrictive bonds with each other and the solid melts. The atoms are still bound by other forces, but if you heat them more, they break free of those too, and the liquid becomes a gas. Heat them more, give them more energy, and the atoms whiz around faster and faster. Heat them to millions or billions of degrees, and the atoms themselves fall apart. They collide so violently, they can overcome the hugely strong forces holding their nuclei together, and you get a soup of subatomic particles, electrons, neutrons, and protons. Heat them more, and even protons and neutrons will collide hard enough to shatter into their constituent subatomic particles, which are called quarks. And as far as we know, quarks and electrons are basic particles, so they can't be subdivided anymore. Maybe you can see where I'm going here. As we wind the clock backwards, the universe gets denser and hotter. At some point in the past, it was so hot that atoms wouldn't have been able to hold on to their electrons. A little farther back, and it was so hot that nuclei couldn't stay together, and the universe was a small, ultra-dense ball of energy mixed with neutrons, protons, and electrons. Go a wee bit farther back, and even that changes. Neutrons and protons couldn't form, because the instant they did, they'd whack into each other hard enough to fall apart. The universe was a sea of electrons and quarks. The cosmos was a bizarre, unfamiliar place back then. Even the basic forces we see today, gravity, electromagnetism, and the two nuclear forces responsible for holding atomic nuclei together, as well as letting them disintegrate in radioactive decay, were all squeezed together into one unified superforce. Like the snowball melting and vaporizing, each of these moments in the history of the universe was like a phase change. The very nature of reality was changing, its laws and behavior different. At some point, we go so far back, so close to that first moment in time, that our laws of physics, well, they don't break down so much as say, here be dragons. We just don't understand the rules well enough to be able to say anything about that first razor-thin slice of time. How far back are we talking here? If we call the instant of the Big Bang times 0, then our physics cannot describe what happens in the first 10 to the minus 43 seconds. Now, let me just say, only semi-sarcastically, that that's not so bad. The universe is 13.82 billion years old, so being able to go back to that very first 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second is a massive triumph of physics. What happened after that fraction of a second is better understood. The universe expanded and cooled. The four forces went their separate ways, and the first basic subatomic particles were able to hold themselves together. This all happened in the very first second of the universe's existence. 3 minutes later, yes, 3 minutes, the universe cooled enough that these subatomic particles could start to stick together. For the next 17 minutes, the universe did something remarkable. It made atoms. It was still ridiculously hot, like the core of a star, but it's at those temperatures that nuclear fusion can occur. For a few minutes, the particles smashed together, forming deuterium, an isotope of hydrogen, helium, and just a smattering of lithium. A little bit of beryllium was made as well, but it was radioactive and rapidly decayed into lithium. Then at T plus 20 minutes, the universe cooled enough that fusion stopped. When it did, there was 3 times as much hydrogen as helium in the universe. This primordial ratio is still pretty much true today. When we measure the sun's elemental abundance, we see it's roughly 75% hydrogen, 25% helium. At this point, the universe is still hotter than a star's surface, but it's also still expanding and cooling. As it does, structures start to form as the gravity of matter can overcome the tremendous heat. These will become the galaxies we see today. This is important and a bit weird, so I'll get back to it in a minute. The next big event happened when the universe was at the ripe old age of about 380,000 years. Up to this point, electrons couldn't bond with the atomic nuclei zipping around. Every time they did, it was so hot that random photons would blow them off again. The universe was ionized. But then, after 380 millennia, it had cooled enough that the electrons could combine with protons and helium nuclei, becoming stable neutral atoms for the very first time. We call this moment recombination. This was an important event. Free electrons are really, really good at absorbing photons, absorbing light. When the universe was still ionized, prior to recombination, it was opaque. A photon couldn't get very far before an electron sucked it up. But after recombination, the photons were free to fly. The universe became transparent. Why is this important? Because the light emitted at this time is what we see as the cosmic microwave background today. Those neutral atoms emitted light. They were as hot as a red dwarf star. Those photons have been traveling ever since, fighting the expansion of the universe, redshifting into the microwave part of the spectrum, and seen today all over the sky. That background glow, predicted by the Big Bang model, has been on its journey to Earth for almost 13.8 billion years. This light is incredibly important because it tells us what the universe was like not long after it formed. For example, that light looks almost exactly the same everywhere you look in the sky. It looks smooth. That tells us that matter was very evenly distributed everywhere in the universe at that time, and also that all the matter had the same temperature. If there had been one spot that was denser, lumpier, then it would have been hotter, and we'd see that in the background radiation as a patch of bluer light. That's pretty weird. When you look at the background radiation from opposite sides of the sky, you're seeing it coming from opposite ends of the universe. Even back then, those regions of the universe were separated by vast distances and had plenty of time to go their separate ways, change in different ways. They should look pretty different, but they don't. As telescopes got better, very tiny variations in the light were found, but they were really teeny, only a factor of 1 in 100,000. In other words, one part of the sky may look like it has a temperature of 2.72500 kelvins, but another spot is at 2.752501. The universe had lumps, but they were far, far smaller than expected. Something must have happened in the universe to force it to be this smooth, even hundreds of thousands of years after the Big Bang. This led theoretical physicist Alan Guth to propose a dramatic addition to the Big Bang model. At some point in the very early universe, the expansion suddenly accelerated vastly. For the tiniest fraction of a second, space inflated hugely, far faster than the normal expansion, increasing in size by something like 100 trillion times. We call this super expansion inflation. It sounds a little arbitrary, but it actually has quite a bit of physical foundation now. In a sense, it's like one of the phase changes of the universe that happened in that first fraction of a second, dumped huge amounts of energy into the fabric of space-time, causing it to swell enormously. Inflation explains why the universe was so smooth at the time of recombination. Space expanded so rapidly that any lumps in it were smoothed out, like pulling on a bedsheet to flatten out the wrinkles. Inflation explains several other problems in cosmology as well. And although the details are still being hammered out, the basic idea is almost, pardon the expression, universally agreed upon by astronomers. The fluctuations we see in the background glow now were actually incredibly small perturbations in the fabric of space at the time of inflation, which got stretched by inflation to macroscopic size. These denser spots were seeds, eventually growing even more, their gravity attracting flows of dark matter. Normal matter collected there too, condensing, eventually forming the first stars about 400 million years after the Big Bang. Eventually, those teeny little bumps from the beginning of the universe became galaxies and clusters of galaxies, now tens of billions of light years away. Our own galaxy, our own piece of the universe, started the same way, as a quantum fluctuation in space 13.8 billion years ago. Now look at us. How's that for an origin story? There are still many unanswered questions in our understanding of cosmology. What's dark energy? What was the role of dark matter in the early universe? Where did the universe come from in the first place? Are there more universes out there, hidden away where we can't see them? If time and space started in the Big Bang, does it even make sense to ask what came before it? Or is that like asking what's north of the North Pole? We don't know the answers to these questions, and trust me, there are thousands more just like them. But here's the fun part. We might yet be able to answer them. After all, even asking if the universe had a beginning, let alone what happened between then and now, was nuts just a century or two ago. Now we have a decent handle on it, and our grip is getting better all the time. Science! Asking and answering the biggest questions of them all. I love this stuff. Today you learned that the timeline of the universe's history can be mapped using modern-day physics and astronomical observations. It started with a Big Bang, when the universe was incredibly dense and hot. Compared to human experience, the universe has been around a long time, nearly 14 billion years. That's a soul-crushingly long time. That's older than Earth, older than the sun, older than, well, everything, pretty much by definition. And yet, when you think about time itself, how long is 14 billion years, really? It seems like a long time to us now, but time keeps on slipping into the future, and every day the universe is a little bit older. I mean, sure, duh, of course it is. But have you ever really thought about what that means? Someday the universe will be 20 billion years old, 30, then 50 billion, 100 billion, a trillion. And even then, the clock still ticks. Those numbers sound abstract, but those days will inevitably come. Time runs long. What will the universe look like in that far, far future? Different. It'll look different. We're about to go on a long journey, literally the longest possible. We're going to the end of the universe. First, a bit of a content warning. The stuff I'm going to show you today is incredibly interesting, incredibly cool, and, well, maybe a wee bit distressing to some people. But I want to say that it's not all darkness and dissolution. Well, to be honest, it's mostly darkness and dissolution. But there is some light, almost literally, at the end of the long, long tunnel. I'm going to have to use some pretty big numbers in this episode. And by big, I mean big. Probably bigger than any numbers you've come across before. I'll have to use scientific notation, which is a shorthand way of expressing numbers using powers of 10. For example, the number 100 is equal to 10 times 10. So we say it's 10 squared, or 10 to the power of 2. 1,000 is 10 times 10 times 10. So it's 10 cubed, or 10 to the third power. This might seem silly for smaller numbers, but it gets useful for much larger ones. A million is 10 to the sixth. A billion is 10 to the ninth, and so on. Mind you, every time the power, the exponent, goes up by 1, the actual number is 10 times bigger. So 10 to the 18th isn't twice as big as 10 to the 9th. It's a billion times bigger. At different times in the life of the universe, different objects dominate. For example, in the current universe, now, you can make the case that stars are the dominant objects. They produce the most amount of energy. Before stars, something else was. Dispersed plasma, I suppose, generally speaking. Astronomers Fred Adams and Greg Laughlin looked at what will happen to the universe on very long timescales and divided it into 5 broad epochs, then wrote about it in their book, The 5 Ages of the Universe, which is a pretty good read. Their divisions aren't official in any way, but I think they did a good job given what we know, so let's use them. First came the primordial era, which we already went over in the last episode. It's basically everything from the moment the universe Big Banged up to when the first stars formed about 400 million years later. The second era is the one we live in now, where stars rule the night. This is the stelliferous era. We're about 13.4 billion years into it. But how long will it last? Or to phrase it another way, when will the last star die? The lower the mass of the star, the longer it will live, steadily fusing hydrogen into helium at a very slow rate. Models indicate the lowest mass red dwarf can do this for about 1 trillion years. That is a long time. A red dwarf that formed when the universe was young would only now have used up about 1% of its hydrogen and has about 99% of its life ahead of it. In human terms, they're still infants. Right now, galaxies are merrily churning away, converting nebular gas into stars. But eventually, that gas will run out. Estimates vary, but star formation in most galaxies will start to peter out in a few billion years. Fewer stars will be born, and the ones already born will start to die off. Galaxy collisions and other events may trigger star formation after that, so maybe they'll extend things a bit. But even if it lasts another 50 billion years or 100, it hardly matters. When the longest star sticks around for 1 trillion years, why quibble about a few billion here and there? As this happens, galaxies will change color and fade. Most spiral galaxies have disks that are a vibrant blue in color, the massive hot luminous stars dominating their emission. But as these stars die and the fainter lower mass stars take over, the galaxy will redden and dim. A few billion years after the nebular gas runs out, the only stars left will be those long-lived red dwarfs. In 1 trillion years, this is what awaits us. It may take longer. I've seen some calculations that show the very lowest mass stars might last 10 times that long. Whatever. I'm not going to worry too much about factors of 10 here or there. As the universe ages, those are essentially statistical fluctuations. But when that does happen, when the last star dies, it means that the only objects left in the universe generating appreciable energy will be the corpses of stars, white dwarfs, neutron stars, and black holes. And to be fair, brown dwarfs as well, those objects intermediate in mass between stars and planets. With the exception of black holes, those objects are supported by various forms of degeneracy pressure. That means in a few trillion years, it'll be the end of the stelliferous era and the start of the degenerate era. The universe will be dark. Dark to human eyes, at least, assuming we have eyes in 1 trillion years, or that we're even around. In the infrared, things are a bit brighter. Many of those objects will be glowing at those wavelengths since they'll be warm. Well, lukewarm. Neutron stars and white dwarfs are born very hot and fade over time. How long that takes depends on how massive they are and other factors, but it's safe to assume that they'll have cooled to room temperature at best in a few trillion years. And the deeper we get into the degenerate era, the cooler they'll be. They'll have their moments, though, because over trillions of years, binary white dwarf orbits will decay, and the stars will merge and explode as supernovae. Binary neutron stars will merge and form gamma ray bursts too. Explosions so bright they'll outshine 1,000 galaxies in this far-flung future. Briefly, these are short-lived events, and soon thereafter, the universe will return to darkness. Interestingly, brown dwarfs are a better bet as an energy source. Binary brown dwarfs could merge to form a relatively normal, if low-mass star that could shine for hundreds of billions of years. But again, time is long. After a quadrillion years, this too shall pass. Stars just ain't what they used to be. In fact, in the degenerate era, neither is the universe. In our dark energy episode, I mentioned that as the universe expands, our view of it will shrink. At the same time, all the galaxies in the local group will collide and merge, forming one big elliptical galaxy. By deep into the degenerate era, all we'll be able to see is our own bloated dark galaxy. The rest of the universe will be forever cut off from us. Not that there'll be all that much to see anyway. And I hate to say this, but even that won't last. Our models of how subatomic particles behave predicts that over very long periods of time, protons, the positively charged particles in the nuclei of atoms, will decay. The half-life of such an event is at least 10 to the 34 years, and it's almost certainly longer. But the degenerate era is longer yet. As protons decay one by one, matter itself will disintegrate. White dwarfs, neutron stars, brown dwarfs, planets, all of them will dissolve as their constituent protons decay. There's an upside, kinda. Adam and Laughlin calculate that proton decay, which releases a tiny bit of energy, will cause white dwarfs to radiate heat with about the energy of 400 watts. Mind you, the microwave oven in my kitchen generates more power, and it's a lot smaller than a white dwarf. But comparatively, in 10 to the 38 years, this will look like a bright star does to us now. By 10 to the 40 or so years from now, even degenerate stars will be gone. The only big objects that will be left are black holes. Thus begins the black hole era. Black holes don't generate a lot of energy unless they happen to suck down a large amount of material that can be torn apart and turned into an accretion disk. Otherwise, basically, they just sit there. However, there is a way black holes can make energy. They evaporate. I know. Most people think that black holes can only eat stuff, and once it's in there, that's where it is forever. Oh, but that's a pesky word, forever. When you're talking 10 to the 50th, 10 to the 60th, 10 to the 90th years, what does forever mean? Back in the 1970s, physicist Stephen Hawking worked out the math of black holes combined with quantum mechanics and discovered that under some circumstances, they can emit particles. This is a very weak effect and has extraordinarily complicated physical mechanisms behind it. Check the doobly-doo for links that explain it. But the end result is that black holes can very slowly leak mass, and the more massive they are, the slower the leak. How slow? A black hole with 3 times the sun's mass, the minimum size for one created in a supernova, will take about 10 to the 68 years to evaporate. That's a ridiculously long time. But the universe can wait. Even supermassive black holes in galactic centers evaporate. It takes them, get this, 10 to the 92 years, 10 to the 92nd power. That number is so huge, so colossally ridiculous, that I can't even come up with an analogy for it. It's a 1 followed by 92 zeros. There aren't even that many subatomic particles in the entire universe. See what I mean? Ridiculous. That's the length of time we're talking here. But it'll happen, eventually. As black holes lose mass, they emit particles and energy faster. So each time one evaporates completely, it'll emit a flare of light, like a small bomb going off. During the black hole era, that'll be the only source of energy in the universe. Eventually, they'll all go away, and that'll be it. There won't be anything else in the universe except subatomic particles and photons, and they'll all be so low energy they might as well not exist. That'll happen pretty much by 10 to the 92 or 93 years from now. At this point, the universe, it's safe to say, is dead. Kaput. Done. We have entered the ominously named Dark Era. It'll stretch to infinity, if time even has any meaning by then. That's awful. I mean, seriously, writing about this and talking about it is hard, because it's not fun to think about this stuff. I mean, it is, kinda, but when you internalize it, it's bleak. There is another idea that would prevent this potentially eternal darkness from happening, but you won't like it much. Dark energy is pumping up the universal expansion, causing it to accelerate. We don't know much about dark energy. We don't even know what it is. We do know that the cosmic horizon, how far out we can see into the universe, is shrinking as the expansion accelerates. One idea among many about dark energy is that its influence will get stronger and stronger. As it does, the horizon will shrink ever faster, closing in on us more and more rapidly. But that's not some illusion. It's a physical limit to the universe, a stretching of space-time. No force, not gravity or electromagnetism or anything, can cross it. It will be as if that part of the universe across the horizon is ripped away from us, stretched beyond breaking. Over time, according to this hypothesis, the cosmic horizon will eventually shrink until it's smaller than our galaxy, smaller than the nearest stars, smaller than the solar system, smaller than our planet, and it'll keep shrinking until it's smaller than a subatomic particle. When that happens, it'll be as if the universe is torn apart at the most fundamental quantum level. Astronomers call this the Big Rip. We have no idea if it will actually happen or not, but if it does, it'll be many billions of years from now, long after the sun dies, but long before the Dark Era. I'm not particularly comforted by this idea, but the good news is that this idea isn't really much more than conjecture. As we learn more about dark energy, we'll learn more about its eventual influence on the fate of the cosmos. Yay? So, is there any reprieve? Maybe. It's possible, though by no means proven, that our universe is one of many universes, a multiverse, if you will. Those other universes may be ticking along just fine, long after ours is wound down. Of course, we can't get to them, but still, good on them. And there's another idea. It's a little far-fetched, but not completely outside the realm of physics as we know it. We think of the vacuum of space as being devoid of energy, empty. But there's an idea in quantum mechanics that this might be an illusion. There might yet be a lower energy state we don't see. Think of it like a staircase. You've been standing on what you think is the bottom step, but then you find out you're actually one step up from that. Our universe may be narrowly balanced on this second to lowest step. It'll stay there, but if something bumps it, down it goes. It's possible that somewhere out in the dead, dark universe, for whatever reason, after a gazillion years, some small bit of space will be quantumly jostled and drop down to that next lower state, the true vacuum. What happens when it does? It'll bump the regions around it, and they'll drop, and so on, and so on. Here's the weird part. Well, it's all weird, but here's the really weird part. Inside this region, the laws of physics get rewritten. How? We don't know. As far as we know, we can't know what happens in there. But in a sense, it'll erase space and time inside it, like poof, gone. Everything changes at some fundamental level we can't even understand. This wave of destruction expands at the speed of light, engulfing all of what remains of the universe. What's left behind in its wake is something new, something different. We literally can't know. This idea actually gives me hope. Think of it as a cosmic reboot. The universe has led a long, long life and lingered an unimaginably slow death. This gives it a new lease, a chance to start over again. Maybe this is similar to how our universe came into being in the first place, as a quantum fluctuation in some other universe, budding off from there to create everything we know. Maybe this has happened before and will happen again, over and again, an infinite number of times. I have to say, I like this idea. If it's true, and we don't know, it's just conjecture at this point, but if it is true, then it's not the death of our one universe. It's the opportunity for the birth of an infinite number more. And that is perhaps the single most hopeful thing I know. Today you learned that our universe's days are numbered.
All right, so turn in that page with the 8 parts on it, and I will give you guys some points.